Okay, in these notes we're going to be discussing derivatives of logarithmic functions. So before we do that, let's kind of recap what we should know so far. We have studied rules, differentiation formulas for taking derivatives, things like the constant rule, that the derivative of a constant times a function is the constant times the derivative of the function. The derivative of an actual constant function is 0. We know power rule. That's when you have a variable in your base and a constant in your exponent. Power rule applies. That allows us to take the derivatives of things like polynomials, radical functions, some rational functions. It kind of depends on what it looks like. We know sum and difference rules. We know product and quotient rules. We know chain rule. We know how to take the derivative of trig functions. We know how to take derivatives of inverse trig functions. So all of these things we have spent a lot of time on. But now the one classification we haven't really gotten to yet is derivatives of exponential and log functions. We have talked about exponentials. We've talked about the fact that the derivative of e to the x is e to the x. That's kind of a special case. In general, the derivative of an exponential that does not have base e would be a to the x times the natural log of a. That of course applies to e to the x as well. It's just that technically this would be getting multiplied times the natural log of e, and the natural log of e is just 1, so we usually leave that out. But what we haven't gotten around to talking about is how are we supposed to take the derivative of a logarithmic function? So we're going to investigate that together. In the end, we'll have an answer on how to do this, but let's kind of walk our way through the process by which we kind of figured out how to take the derivatives of these. So we're going to start with f of x equals the log base a of x, and we're going to require that a be a legal base for a logarithm. So a has to be strictly larger than 0, a can't be 1. So at the moment, we don't know how to take its derivative. So we do what every good mathematician does. We start with what we do know. What we do know is that when you're talking about a logarithmic function, you can rewrite it in an exponential form. If you have y equals the log base a of x, that is interchangeable with saying a raised to the y power equals x. So if we're able to switch and instead of dealing with it in logarithmic form, deal with it in exponential form, that's great. We know how to take the derivative of an exponential. So what we need to do is take the derivative of a to the y equals x, but here's the sticky part, it's with respect to x. So if you're going to do that, notice you've got a y up here in the exponent, which means what kind of technique of differentiation are you going to have to use? Well, there's an entire function sitting up in that exponent. This is implicit differentiation. So if we differentiate a to the y equals x using implicit differentiation, the derivative of a to the y contains an a to the y times the natural log of a, because that's the natural log of our base. But because y is a function of x, and this is implicit differentiation with respect to x, we need to take the derivative of the exponent, which we're just going to call dy dx. And then the derivative of x with respect to x is just 1. And like all other implicit differentiation examples that we've done, we then solve for dy dx. We get 1 over a to the y ln a. But again, we would really like this to have everything in terms of x. Right now, we've got it in terms of y, and because this is with respect to x, we'd like it to be in terms of x. So you can either say, okay, well, y is the log base a of x, which is what I have written here, at which point this part would simplify, because when the base of the exponential and the base of the log are the same, they cancel each other and just leave you with x. Or you can look back up at this line and say, look, a to the y, it is replaced by x. Either one's a correct thought process. So in other words, based on our investigation, what we just figured out is that if you want to take the derivative with respect to x of the log base a of x, remember that makes a constant, x is your variable, the way you do that is you take 1 over x, and in the denominator you're multiplying that times the natural log of a. So if we start off simple, let's say we wanted to differentiate f of x equals the log base 6 of x. Then your derivative, based on our differentiation formula right above, is going to be 1 over x times the natural log of the base, and the base in this case is 6. If we up the difficulty level just a little bit, let's say we wanted to take the derivative of the log base 6 of sine x. So sine x, this is not multiplication. Sine x is an input into your log function. If we meant this to be multiplication, we would have written the log base 6 of x. We would have had to have put an input in there times sine x. This would be multiplication, not this one. This is a composition, which means it's a chain rule. So its derivative will be found by taking, instead of 1 over x, we need 1 over the inside function as is. 1 over sine x times that natural log of 6. Okay, because 6 is still our base for this one. So this is the derivative of the outside part. We then multiply times, this is chain rule, times the derivative of the inside function. And the derivative of sine x is cosine x. So usually you're just going to see that written as cosine x over sine x ln 6. And feel free to skip this middle step. You can go straight to the end once we get a little more practice. So that brings me to the example where we're taking the derivative of the log with the base that we most commonly use in applications in physics and engineering. More often than not, you're using base e more than any other base. So when you take the derivative of the natural log of x with respect to x, if you follow this pattern, what you're going to get is 1 over x, and then times the natural log of the base of your log, but the base of that is e. And yes, the natural log of e is 1. So in other words, the derivative with respect to x of the natural log of x is 1 over x. That's one you're pretty much going to want to have committed to memory. That shows up extremely frequently. If you combine it with chain rule, what we get is when you're taking the derivative with respect to x of the natural log of u. Remember, this is with respect to x, which means u represents an entire function. You get 1 over the function, you leave that inside function as is, times the derivative of the inside function. If you prefer the other type of notation we use for chain rule, that would say that if you had the derivative with respect to x of the natural log of the function g of x, you'd have 1 over g of x times the derivative of g of x, or g prime of x, so that would go in your numerator. It's the same thought process, just two slightly different notations. Let's look at a couple of examples. Let's differentiate y equals the natural log of t cubed plus 1. So when we differentiate this one, you can call it y prime. This one's with t, so if that happens to be time, by the way, in physics the way they write that is y dot. If we do use Leibniz notation, that would be dy dt. So it's, even though we switched off to t instead of x, it's the same process. It's 1 over your inside function being t cubed plus 1, now times the derivative of the inside function, but I'm going to go ahead and just write it in the numerator and save my steps. And the derivative of t cubed plus 1 is 3t squared plus 0, which I'm not going to write. So that's my derivative. Now let's take a look at this one. This is the derivative with respect to x of the natural log of x plus 1 divided by the square root of x minus 2. Now, if we use the differentiation formula that we just talked about, we could correctly find this derivative by taking 1 over the inside function. So that's 1 over x plus 1 over the square root of x minus 2. And yes, that would flip that fraction if you were to simplify it. And then you would need that times the derivative with respect to x of the inside function. So times the derivative of x plus 1 over the square root of x minus 2. There is absolutely nothing incorrect about this, but take a look at this derivative you're about to have to take. That's not particularly pretty. It involves quotient rule. It also, when you take the derivative of the denominator, is going to involve chain rule. So while it's not incorrect, it is not particularly fun. So believe it or not, in this kind of situation, it's actually a bonus to have a logarithm in this derivative. We're going to make some really good use of that. Instead of taking the derivative of this function as written, I'm going to use the properties of logs first. I can instead take the derivative of, notice this is the natural log of two things being divided. Well, according to properties of logs, that's going to be the natural log of x plus 1 minus the natural log of the square root of x minus 2. So already right there, I've gotten rid of my quotient. So that's a bonus. But in addition to that, notice this square root. Remember, that's the same thing as having an exponent of a 1/2. And remember what you get to do with exponents when you're talking about logarithms. You get to drop them down as coefficients. So this is the natural log of x plus 1 minus 1/2 the natural log of x minus 2. That is as far as you can go in simplification. Please remember this does not equal the natural log of x plus the natural log of 1. Okay, logarithms do not distribute. But now that I have it in this form, that derivative is a lot easier to take. The derivative of the natural log of x plus 1 is 1 over x plus 1 times the derivative of x plus 1, which is just 1, minus 1/2. Now I need the derivative of the natural log of x minus 2, so that's 1 over x minus 2 times the derivative of x minus 2, which again is 1. So I mean, I can clean that up a little bit, but that's pretty much it. It's 1 over x plus 1 over minus 1 over 2 times x minus 2. And there you go. That is way easier than dealing with the quotient and chain rule that I would have had to have done had I gone the more traditional route. So when you are taking the derivative of a logarithmic function, keep an eye out for that. That's always legal to use those properties first. So we have some other ideas to talk about when we talk about the derivative of logarithmic functions. But before we do that, let's pull some ideas together that we've already talked about. But I just want to make sure that we just kind of take a look at them all in at the same time. If we take the derivative with respect to x of a to the n, and this is why I've been really careful to make sure you've got to keep an eye on what's a variable and what's not. This is the derivative with respect to x, so x is your variable. Do you see any x's in here? No, which means a is a constant and n is the constant. So what is the derivative of any constant? Well, it's 0, okay? This one had no variables whatsoever, okay? So that one was nice and straightforward, as long as you knew to look for the x. If we look at this one, this is the derivative with respect to x of a function raised to the nth power. So again, x is my variable according to my derivative. Notice that is in the base, and I have an n in the exponent, which means this has a variable in the base and a constant in the exponent, which tells me which of the rules I need to use to take the derivative. When there's a variable in the base and a constant in the exponent, that's a power rule. Once I know that, I just have to correctly apply it. We drop the n down as a coefficient. This is an entire function inside there, so we don't touch the inside function. This is going to be chain rule. We subtract 1 from the power, and then we multiply times the derivative of the inside function. Okay, so that's what it looks like for our power rule. When we look at this one, this is the derivative with respect to x of a to the f of x. Notice this time, x is still my variable, but the variable is now in the exponent, and a is a constant because it doesn't have an x in it. So because I have a variable in the exponent and a constant in the base, it tells me that if I want to take this derivative, I need to use our rule for exponentials. So the derivative of an exponential contains that exponential as is, a raised to the f of x, times the natural log of that base. This is not base e, so this is times the natural log of a. That is considered the derivative of your outside function. Then times the derivative of the inside function, which is your exponent, so f prime of x. So that's our rule for exponentials. Once we have an eye on those, let's take a look at this one. We've got the derivative with respect to x of f of x raised to the g of x. So now this is both a function in the base and in the exponent, which means you have a variable in the base and a variable in the exponent. If I have variables in both places, how am I supposed to know which rule to use? Do I use the power rule because the variable's in the base? But wait, to use power rule, I'm supposed to have a constant in the exponent. Okay, well maybe I should use the rule for exponentials. But in order to use the rule for exponentials, you're supposed to have a variable in the exponent and a constant in the base, and I don't have that. I have neither one of those. So how am I supposed to know which rule to use? Well, it turns out you can't use either one. If you see a variable in both the base and the exponent, and I gave an example here. So for example, if you were taking the derivative of something like x raised to the square root of x, you can neither apply power rule nor can you apply the rule for exponentials. So now how are you supposed to take the derivative of this? Well, turns out you've got two options. The first option is what we refer to as logarithmic differentiation. And what logarithmic differentiation suggests that we do is say, okay, well, you've got this function y equals f of x. So I'll pull the example from the previous slide. Y equals x raised to the square root of x. This is still a function of x. It's just that I'm seeing the variables in both base and exponent. What we can do is actually purposely introduce a log into this equation. Now we do have to treat it as an equation because what I want to do is take the natural log of both sides. Now remember, you can't just take a natural log because you feel like it. You have to make this equivalent somehow. So as long as you take the natural log of both sides of an equation, it's legal. And then what you want to do is use the properties of logarithms to simplify that equation. And the main one I'm interested in is the property of logs that allows me to take exponents. If it's inside a log, I'm allowed to take this exponent and drop it down as a coefficient. So that's actually why you would be interested in introducing a logarithm into this, because logarithms take exponents and turn them into coefficients. So that's kind of where we're heading with this. Once you have that, we're still looking to take the derivative with respect to x. And notice if you've got this equation and you want to take the derivative with respect to x, you have to take the derivative of both sides, which means you're using implicit differentiation. And then because you're using implicit differentiation, you need to make sure you're solving for dy dx. So let's go ahead and do this particular one. So we'll write it as the natural log of y equals the natural log of x raised to the square root of x. Now this is inside your log, so we get to drop that square root of x. So this becomes the natural log of y equals the square root of x times the natural log of x. Okay, I haven't done any derivative taking at all yet. All I've done is use properties of logs after introducing a natural log on both sides. Now I'm going to take a derivative, but it's of both sides of your equation. The natural log of y, when you take its derivative with respect to x, it's 1 over, don't touch your inside function, so that's y, times the derivative of the inside function, which we're just going to call dy dx. And then on the right-hand side, everything is with respect to x anyway, so we're going to go ahead and just use our product rule over here. So the derivative of the square root of x is 1/2 x to the negative 1/2. By product rule, we need to leave the natural log of x alone, and then add to that the square root of x as is, x to the 1/2, times the derivative of the natural log of x, which is 1 over x. Okay, I'm going to clean that up a bit as I solve for dy dx. So when I solve for dy dx, notice the only thing that's sitting over here is this 1 over y. So multiply both sides of the equation by y. I'll just leave that there for right now. The first term, I'm going to put the x to the negative 1/2 in a denominator. The natural log of x is going to stay up in the numerator. So it's natural log of x divided by 2 square root x, the 2 comes from the 1/2, plus, when you take x to the 1/2 times 1 over x, that should give you x to the negative 1/2, or 1 over the square root of x, either way. Okay, now we don't quite want to leave it like this. We're most of the way there, but we don't want to leave it like this because again, it's dy dx. I'd like everything to be in terms of x, so I don't want a y sitting here. So all I have to do though is just replace the y with the x square root x. So I will get x raised to the square root of x times the natural log of x over 2 square root y plus 1 over the square root x. And you could do things like getting common denominators and things like that, but it's not necessary in order to have the correct derivative. Okay, so that's our first option, logarithmic differentiation. So in a nutshell, what it involves is treating your derivative as an equation and taking the natural log of both sides and then taking advantage of the properties of logs and using implicit differentiation. Okay, so keep that in mind when we move to option 2. So option 2 also is going to ask us to rewrite our function, but instead of taking the natural log of both sides of an equation, This one's going to allow you to instead just rewrite your function. You're still going to introduce a natural log into this, but the way you're going to essentially introduce it without dealing with both sides of an equation is to use your cancellation equations. I mean, we know that when you have the base of an exponential raised to the log with the same base of anything, what you get is that anything. That's your cancellation equation. So we're going to take advantage of that. Instead of dealing with y equals x raised to the square root of x, and instead of taking the natural log of both sides, I'm only going to rewrite the right-hand side. I still want a natural log in here because that's how I'm going to get this square root of x out of the exponent. So what I'd love to have is that ln of x raised to the square root of x. But you can't just do that. You have to keep this equivalent. So the way you do that is you put an e in a base. Now these two are equivalent. And now you can actually continue to use that same property of logs that says I can take this square root of x, which is in an exponent, and drop it down as a coefficient instead. The difference is the coefficient and the log are now in the exponent of a base e. But I know how to take the derivatives of those. And what this is essentially going to do is make it so that I don't have to use implicit differentiation, because everything is with respect to x. When you take the derivative of y with respect to x, there's your dy dx. And the right-hand side, it's an exponential, so it will still contain the same exponential you start with. Technically, this is now times the natural log of e, but because the natural log of e is 1, I'm not going to write it. And then I need it times the derivative of the exponent. So that's going to be another product rule. It's the same product rule we just did. The derivative of the square root of x is 1/2 x to the negative 1/2. Leave the second function alone for product rule, plus x to the 1/2 times the derivative of the natural log of x, which is 1 over x. And if you notice, that's exactly the same thing I just had on the previous slide. You're looking at ln x over 2 square root x plus 1 over the square root of x. The only cleanup you're going to want to do is notice you have e to the x ln x sitting out here. You don't need to write it like that any longer. It's served its purpose. You can get rid of the cancellation equation. So here it is sitting here. If you go back 2 steps, remember that was equivalent to x square root x. So that is dy dx for this particular example. So those are your two options. So when you run into a function for which you want to take the derivative and you see a variable in both the base or the exponent, these are your two options on how to make that happen. If I can make a recommendation, I would recommend the second option more often than I would recommend the first one, simply because when we go to work with some of our limits in future sections, you're going to see this technique again. So it's just a suggestion so that you can familiarize yourself with the technique a little bit earlier than you absolutely necessarily have to, so that you can use it when we move into further sections.